In this chapter, we study the warehouse layout design problem. The goal is to redesign a distribution center so that pickers travel less, congestion is reduced, and the overall fulfillment flow becomes smoother. We focus on MegaCorp Distribution, which operates a 200,000 square foot facility that processes 15,000 orders per day. The current average pick time is 8.5 minutes per order, and analysis shows there is significant room for improvement. The current warehouse follows a traditional I-shaped flow. Receiving is located at the north end, shipping is at the south end, and storage is arranged in parallel aisles in between. This design creates long travel paths because fast-moving and slow-moving areas can be far apart, and it creates cross-traffic congestion at aisle intersections. Centralized value-added services also add extra material handling movements. Time and motion studies show that warehouse associates spend about 60% of their time traveling between pick locations. The longest routes require traversing nearly the entire facility length. This is not just inefficient, it also increases fatigue and variability. It makes it harder to meet service targets during peak periods, and it makes future automation harder to implement. Management sets 3 explicit targets for the redesign. First, reduce average pick time by at least 25%. Second, improve space utilization by 15%. Third, build a layout that can flex with seasonal inventory shifts and future automation. The redesign must respect the existing building footprint. So the core decision is how to place receiving, storage zones, picking paths, packing stations, and shipping docks to minimize travel and remove bottlenecks. We will use 5 tiers in this deck. Tier 1 builds a formal assignment model that maps functional areas to candidate locations with capacity and adjacency rules. Tier 2 implements a classic heuristic with randomized construction and local swap improvement. Tier 3 upgrades to a hybrid genetic algorithm and variable neighborhood search. Tier 5 uses a digital twin for continuous adaptation. Tier 7 adds a human and artificial intelligence Centaur partnership with explainable recommendations. Tier 1 models the layout as a constraint satisfaction and optimization problem. You assign each functional area, like receiving or packing, to one location in a grid of candidate positions. The objective is to minimize flow-weighted travel distance. That means high-volume material flows should be placed close together in rectilinear distance, while still satisfying capacity limits and required adjacencies. This slide defines the sets and parameters. Functional areas include receiving, storage zones, picking and packing, shipping, and supporting functions. Candidate locations are grid positions in the warehouse, each with coordinates and an available area capacity. We define flow intensity between areas as units per day, and we define rectilinear distance between locations as horizontal plus vertical movement. These pieces connect operational reality to the layout decision. The key decision variable is a binary assignment indicator. It is 1 when a specific functional area is placed in a specific location and 0 otherwise. Once those assignment indicators are chosen, the model can compute which flows, travel which distances, and it can evaluate feasibility against the constraints. The objective minimizes the total material handling effort. For every pair of functional areas, we multiply the daily flow by the distance between the chosen locations. This objective is valuable because it naturally prioritizes high-impact flows. If receiving to fast storage moves hundreds of units per day, placing them close produces much larger savings than optimizing a low-flow connection. The assignment constraints ensure the layout is well-defined. Each functional area must be assigned to exactly one location. At the same time, each location can host at most one major functional area. These constraints prevent ambiguous layouts and prevent overlaps that would be impossible in the real facility. Capacity constraints connect space planning to feasibility. Each location has a maximum area, and the functional area you place there must fit. This prevents solutions that look good in distance but are impossible because a high-volume operation, like packing, is squeezed into a location with insufficient area. Adjacency requirements handle like operational dependencies. Some functions must be near others, such as packing near shipping or receiving near returns processing. The constraint states that when one area is placed at a location, the paired area must be placed in the neighborhood around that location. This prevents layouts that minimize distance in aggregate but violate practical workflow needs. This visualization shows how the warehouse can be structured into zones and connected flows. The key idea is that slotting and layout should be designed around dominant flows and congestion points. In practice, this means clustering high-flow operations and designing paths that reduce cross-traffic and backtracking. Now we walk through a concrete example. There are 4 functional areas and 6 candidate locations arranged as a 3x2 grid. Daily flows are 850 units from receiving to storage, 600 from storage to packing, and 600 from packing to shipping. The reported optimal assignment yields a total weighted distance of 2,900 unit distance per day. A linear, I-shaped alternative yields 3,400, which is about 17% worse. Tier 2 moves from exact optimization to a practical heuristic. First, we construct a feasible assignment using flow-weighted preferences, which means we try to place strongly connected areas closer. Then we apply local improvement by swapping pairs of areas and keeping swaps that reduce total weighted distance. Randomization helps avoid being trapped in a single deterministic pattern. This workflow figure shows the 2-phase structure: construction and improvement. The construction step creates an initial layout quickly. The improvement step evaluates neighbor layouts created by swaps and adopts the best improvements. This structure is common in practical layout and routing heuristics because it is simple, fast, and effective. This slide summarizes computational effort. The construction phase evaluates area to location options, and the improvement phase evaluates many possible swaps. The reported simplification is that the swap improvement effort grows roughly with the 4th power of the number of areas. That is still workable for typical warehouse layouts with around 10 to 20 areas. In this part, we move from the idea to the mechanics of the implementation. The key class visible here is the Warehouse Layout Optimizer class. Key functions in this chunk include initializer and randomized construction. As you read it, focus on the sequence of steps and which variables are carried forward, because that is where most implementation bugs hide. Also check stopping rules and guardrails so iterative logic stays stable and does not drift. A practical check is to print or log a few intermediate quantities so you can verify that the update logic behaves as expected. In this part, we move from the idea to the mechanics of the implementation. Key functions in this chunk include local improvement. As you read it, follow the data flow from inputs to outputs and pay attention to how the state is updated. Also check stopping rules and guardrails so iterative logic stays stable and does not drift. A practical check is to validate this chunk against a small hand-computed example so you can trust it before using it in production. In this part, we move from the idea to the mechanics of the implementation. Key functions in this chunk include evaluate solution. As you read it, track what is computed, what is stored, and what gets updated each iteration. Also check stopping rules and guardrails so iterative logic stays stable and does not drift. A practical check is to print or log a few intermediate quantities so you can verify that the update logic behaves as expected. In this part, you can see the implementation details in action. Key functions in this chunk include optimize layout. You will notice logic related to iteration. As you read it, follow the data flow from inputs to outputs, and pay attention to how the state is updated. Also check stopping rules and guardrails so iterative logic stays stable and does not drift. A practical check is to validate this chunk against a small hand-computed example so you can trust it before using it in production. In this part, we move from the idea to the mechanics of the implementation. You will notice logic related to iteration. As you read it, track what is computed, what is stored, and what gets updated each iteration. Also check stopping rules and guardrails so iterative logic stays stable and does not drift. A practical check is to run this section on a tiny test case and confirm intermediate values before scaling up. In this part, we move from the idea to the mechanics of the implementation. As you read it, focus on the sequence of steps and which variables are carried forward, because that is where most implementation bugs hide. Also check stopping rules and guardrails so iterative logic stays stable and does not drift. A practical check is to print or log a few intermediate quantities so you can verify that the update logic behaves as expected. This slide summarizes the example outcome for the heuristic approach. The reported result is a U-shaped configuration that clusters high flow areas and achieves a 28% reduction in total weighted travel distance compared to the original I-shaped layout. Tier 3 improves solution quality by combining a genetic algorithm with variable neighborhood search. The genetic algorithm explores the global space of layout permutations. Variable neighborhood search then intensifies around good candidates using multiple neighborhood structures. This combination helps avoid premature convergence while still producing a refined final layout. This figure illustrates the hybrid architecture. Genetic evolution maintains a population of layouts and uses crossover and mutation to generate new candidates. Variable neighborhood search applies systematic local refinement to the best candidates. In layout problems, that local refinement often provides a large share of the final performance gain. In this part, we move from the idea to the mechanics of the implementation. The key class visible here is the Hybrid Layout Optimizer class. Key functions in this chunk include initializer, evaluate layout, initialize population, and greedy construction. You will notice logic related to mutation, crossover, population, iteration. As you read it, follow the data flow from inputs to outputs, and pay attention to how the state is updated. Also check stopping rules and guardrails so iterative logic stays stable and does not drift. If feasibility is enforced with penalties or repair steps, confirm the penalty scale is large enough to prevent invalid outputs from looking attractive. A practical check is to run this section on a tiny test case and confirm intermediate values before scaling up. In this part, the code makes the slide method executable. Key functions in this chunk include swap mutation, variable neighborhood search, shake, and local search. You will notice logic related to mutation, crossover, population, iteration. As you read it, follow the data flow from inputs to outputs and pay attention to how the state is updated. A practical check is to run this section on a tiny test case and confirm intermediate values before scaling up. In this part, you can see the implementation details in action. Key functions in this chunk include demonstrate hybrid optimizer. You will notice logic related to mutation. As you read it, track what is computed, what is stored, and what gets updated each iteration. If feasibility is enforced with penalties or repair steps, confirm the penalty scale is large enough to prevent invalid outputs from looking attractive. A practical check is to print or log a few intermediate quantities so you can verify that the update logic behaves as expected. The reported results show substantial improvement. The hybrid method achieves 3,850 unit distance per day in a 7-area case. This is reported as 35% better than the classical heuristic and 42% better than the original I-shaped layout. Operationally, the layout reduces picker travel by about 28 minutes per 100 order batch, and it is associated with annual labor savings of about $2.1 million. Tier 5 introduces an integrated digital twin. Instead of optimizing a static layout, the digital twin keeps a real-time virtual representation of the warehouse and continuously evaluates layout scenarios under changing conditions. This includes seasonal variation, new product introductions, automation changes, and workforce shifts. The digital twin enables you to test changes virtually and implement them only when the expected benefit is clear. This architecture diagram shows the digital twin as a system of systems. Sensors and identification technologies feed real-time data into analytics and machine learning layers. Optimization engines then generate recommendations, and visualization and decision support tools help managers understand the trade-offs. This closes the loop between the physical warehouse and the digital model. In the concrete example, MegaCorp integrates over 500 sensors and 50 RFID readers and connects to 8 external systems. The twin processes about 2.3 million data points per day. During the back-to-school season, demand increases by 340% for seasonal items. The system simulates 15 reconfigurations, relocates 2,400 seasonal stock-keeping units, and reports a 23% reduction in pick time, a 31% improvement in space utilization, and an 18% decrease in overtime. The reported payback is 14 months. Tier 7 is the Centaur model, a human and artificial intelligence partnership. Humans contribute context, safety, and practical implementation constraints. AI contributes high-speed computation and scenario exploration. Explainable recommendations are critical so that humans can validate why a layout is suggested and how sensitive it is to assumptions. This diagram shows bidirectional collaboration. Humans define objectives, constraints, and feasibility considerations. AI generates alternatives and explains reasoning through transparent analysis. The best results come from iteration. Humans identify missing constraints and implementation barriers, and AI quickly recomputes the best alternatives under those updated constraints. In the example, the team evaluates multiple alternatives and finds that one top design would require relocating an electrical distribution panel. Human review identifies 3 weeks of downtime and $150,000 in extra cost. The AI then incorporates that constraint and selects an alternative that still delivers a 26% pick time reduction and a 16% improvement in space utilization. Post-implementation results report a 27% improvement in pick time and a 17% improvement in space utilization. These practice questions help you apply the full toolkit. Tier 1 questions focus on writing the complete model and computing assignments. Tier 2 focuses on implementing a heuristic and estimating performance. Tier 3 focuses on designing hybrid meta-heuristics and tuning parameters. Tier 5 asks you to design a digital twin and estimate data volumes. Tier 7 asks you to define roles, protocols, and success metrics for a human and artificial intelligence partnership. The key takeaway is that layout design is largely a travel and congestion problem. If you align zones with dominant flows, you reduce wasted movement and variability. Tier 1 provides a rigorous baseline model. Tier 2 provides a fast, implementable heuristic. Tier 3 improves quality through global search plus local refinement. Tier 5 and Tier 7 extend the approach to continuous adaptation and explainable decision-making in the real world.